In this part, we will be looking at more reactions of alcohols. Previously, we have seen the Grignard reaction, and we've seen also how alcohol can actually be made through those reactions, whether it's a Grignard to generate alcohols or reduction of carbonyl to generate alcohols. We've seen alcohols also as reactants in oxidation reactions, and how alcohols can also act as a nucleophile or electrophile. Nucleophile by generating an alkoxide upon treatment with base, and electrophiles by transforming the alcohol to a good leaving group such as tosylate or mesylate. We've seen the diversity of the tosylate chemistry, how it can give me access to a lot of functional groups. So in this part, we will see how we can generate alkyl halides. We'll see also how we can make esters and some other reactions of diol oxidation and so on. So the very first reaction is with acids. And when we say about acids, we're talking about the source of H plus to protonate the OH. So here's the general equation. Alcohol in presence of H plus, what's going to happen? The oxygen will be basically the lowest base. So it's going to abstract the hydrogen. So it's going to donate an electron. So that's going to basically give me the protonated alcohol, which is the oxonium. This oxonium now is going to have a good leaving group, that is water. So we went from a structure that has a bad leaving group to a structure that has a good leaving group. What's going to happen next? Well, if there is a nucleophile around, such as a halide, that's going to attack R and kick off H2O in the case of a primary alcohol. But in the case of secondary or tertiary, what's going to happen, you're going to generate a carbocation. And we will see the full mechanism actually of this reaction. And it is a required mechanism. So once that halide ends up basically substituting H2O, you're going to end up making the alkyl halide. So the reaction of alcohol with HBr as an example. You see here that the OH being replaced with Br. So how did that happen? Well, the OH will be protonated to give you OH2 plus. OH2 plus will leave basically in the case of tertiary and secondary to give a carbocation. That's why it's going to be an SN1 pathway. So this carbocation formation step only happens when I have a secondary or tertiary alcohol. Whether I have an HCl or HBr or HI, it doesn't matter, because that protonation step, it will be the same for all of them, but the carbocation formation will only happen when I have a secondary or tertiary alcohol. And that's why we say primary alcohol react via SN2. So you're not going to have a carbocation formation in the case of a primary alcohol. And that's important to keep in mind. So here's the full mechanism of the SN1 pathway. So here's an example of a tertiary alcohol, terbutyl alcohol. The very first thing is going to happen when you react with HBr is the protonation step. And usually it's a quick step. So the rate determining step is the formation of the carbocation, not the protonation step. So the first arrow pushing will go from the oxygen toward the H, kicking off Br as a Br minus. So you end up making the oxonium ion, which is the activated alcohol structure. When we say activated, that means we have a good leaving group now. What's going to happen? Well, because it's a tertiary carbon, it prefers to have a carbocation rather than be attacked with a nucleophile. Think of it, it's too crowded for the nucleophile to attack. So that's why faster the carbocation formation will happen. So that's why this will take place only if you have a secondary or tertiary carbon. And that's why you're going to see the carbocation formation here, the case of the tertiary alcohol. And this tertiary carbocation, it's the most stable form of this structure. That basically brings up a point that if I have the chance to generate a more stable carbocation, that additional step will take place before the nucleophile attacks. Meaning 1,2 hydride shift, 1,2 methanide shift are possibilities for this mechanism. So the last step would be basically the Br minus attacking the carbocation. So where did this Br minus come from? It's the very first step where the protonation of the alcohol took place. That's where the Br minus actually got generated. And this Br minus will attack the carbocation I will end up giving you the alkyl halide. So it's an SN1 pathway when you have a secondary alcohol or a tertiary alcohol. What happens if I have a primary alcohol? Well, it will be two-step process. The first step will be the protonation. So here's an example. So you have a butanol attacking HBr. So it's going to be the same arrow pushing where it starts. Oxygen attacks the hydrogen. So that's going to be the step to give you the oxonium ion. And that's the protonated primary alcohol. What's going to happen next? Am I going to get a carbocation? No. Why? Because a primary carbon is considered to be a species that's going to give an unstable carbocation. So it wouldn't go that path. So what's going to happen instead, the Br minus will attack the primary carbon, kick off H2O, and that's how you end up making the alkyl halide from a primary alcohol. Keep in mind, HX, whether I have an HCl, HBr, or HI, will go through the same pathway. SN1 for secondary and tertiary alcohol, and SN2 for a primary alcohol. How about HCl? Because of the fact that Cl minus is a weaker nucleophile than Br minus, that's going to make this reaction even slower compared to HBr and HI. So that's why you will notice that some reactions with HCl, you will see a Lewis acid being used, which is zinc chloride. What is zinc chloride going to do? It's going to activate the alcohol to make it easier to be kicked out. And let me tell you this now. Later on, you will see better methods how to generate an alkyl halide from a primary or a secondary. So this method using HX, it does only apply on tertiary alcohol, actually, because tertiary alcohol tend to be the one that's going to give me the corresponding alkyl halide the fastest way compared to secondary or primary. So how am I going to do primary and secondary alcohol to give a primary or secondary alkyl halide? We will see these methods next. So if I have a primary alcohol, it tends to react very slow, not at all. And if I have a secondary alcohol, it reacts in 1 to 5 minutes, but the tertiary alcohol tends to have actually a very quick rate. When we throw in HCl, doesn't need actually the zinc chloride, but if it does, makes it even faster. The condition of HCl with zinc chloride, it's called Lucas test. So the Lucas reaction, when you hear this name, always think of zinc chloride being used with HCl. Now, not HCl by itself. So here is the mechanism. When I have zinc chloride being used, whether it's a primary or second, but usually the tertiary doesn't need the zinc chloride. But let's say I throw in the zinc chloride. What will take place? Well, the very first step will be that the OH attack the zinc chloride. So that's a Lewis acid, Lewis base reaction. This Lewis acid will be the zinc chloride, and the Lewis base will be the alcohol. Oxygen attacking zinc, that's going to give me this complex. This complex now, it's much more reactive compared to alcohol. So what's going to happen? Well, it's a primary, so it's not going to give it the chance to form a carbocation. What if I have a secondary? It will give me a carbocation. What if I have a tertiary? It will give me a carbocation. But as I mentioned, zinc chloride, usually it's used in the case of primary alcohol because that's where the reactivity need to be boosted, need to be actually pushed to get you the alkyl halide, and that's why the zinc chloride is being used. Cl minus will attack carbon, and this basically kicks off the O zinc. So we can see here the transition state, it's an SN2, so there's no intermediate. The transition state basically generate eventually the alkyl chloride, primary alkyl chloride. And let me repeat, there are other methods that are better than using HCl or HBr when I have a primary alcohol or a secondary alcohol that I want to get a primary or secondary alkyl halide, and we will learn those next. This reaction tends to be very slow. It can take from several minutes to several days. What is that going to depend on? The alkyl alcohol itself. Even if it's a primary, the more sophisticated the primary alcohol is, the slower the reaction will be. So that's important to keep in mind. Here is the the case of SN1 pathway, even if I use zinc chloride, it will be the same route, the first step. Oxygen will attack zinc. That will give me basically this complex, and this complex will not wait for the nucleophile to attack the carbon. What's going to happen instead? Generating the carbocation. So now we see that if I have HX, or if I have HX with zinc chloride, I will form the carbocation in the case of secondary and tertiary alcohol. This is an example of a secondary alcohol, as you see. This secondary carbocation now is going to be attacked by the Cl minus, and this is going to give me the alkyl chloride plus the side product, which is going to be the OH attached to the zinc chloride. The strong bond between zinc and oxygen, what pushes actually the reaction to go forward. And that favored bond is what helps weaken the CO bond to basically end up having the halide substituting the oxygen bond. Limitations usually tend to be a poor yield, and especially if I have a primary or secondary alcohol. Elimination is a problem that you may end up having an alkene instead of a substitution. Of course, because of the formation of carbocation in the case of secondary and tertiary, there is a possibility of rearrangement. So that's but what actually forces us to find alternatives when I have a primary or secondary alcohol to be converted to their alkyl chloride or halide. Here's a question. I have a secondary alcohol reacting with HBr. The question is, justify the outcome. The outcome, as you've seen, that Br is not substituting that carbon where the OH is attached. A substitute is actually attached to the adjacent carbon. So this is a tertiary halide, even though I'm starting with a secondary alcohol. What is exactly happening here? Well, the very first step will be the protonation. So you have OH attacking H+. So that's going to give me the protonated alcohol. That's the oxonium ion or intermediate. This intermediate, because it's a secondary carbon that's attached to the H2O, is going to give you a carbocation. And this secondary carbocation is going to pause and look and say, oh, wait a minute, I can be giving a more stable carbocation. And that will be basically pushing it to go through a 1,2 hydride shift, because the adjacent carbon, it's a tertiary carbon. If you take that hydrogen and do a 1,2 hydride shift, you're going to end up making a tertiary carbocation. And that will be the one that's going to be lower in energy, more favored to go to the next step, which is the halide attack to give you the tertiary alkyl bromide. So that's important to keep in mind, that the reaction of HX with any type of alcohol will always give you a carbocation if you have a secondary or tertiary, but it will be a poor yield if it goes through a primary alcohol getting into the primary alkyl halide. Here's the alternative for primary and secondary. If I have a primary or secondary alcohol, the method of choice will be using PCl3 if I'm interested to make alkyl chloride, using phosphorus tribromide if I'm interested to make alkyl bromide, and using phosphorus iodine if I'm interested to make alkyl iodide. How come not PI3? Well, PI3 is not stable. We can't actually make it and put it on the shelf. It does get ruined over time. Therefore, it's best to make it in situ. So that's why we have phosphorus and iodine. That's the source of PI3. So the alkyl chloride, for a tertiary alcohol, I will just use HCl. For a secondary alcohol or primary alcohol, I will use PCl3. Sometimes you can find thionyl chloride, which is SOCl2, can also be used. In fact, it's better, and we will see the mechanism for it. Alkyl bromide, if it's a tertiary alcohol, then I use HBr. If it's a secondary alcohol or a primary alcohol, I use phosphorus tribromide. It's very important that we put these down to propose them when I need to do a synthesis question. Alkyl iodide, if it's a tertiary alcohol, I will use HI. If it's a primary or secondary alcohol, I will use phosphorus/iodine. That will be the source of PI3 to get me the alkyl iodide from secondary or primary. Here's some examples. So you can see here's a primary alcohol reacting with PPR3 that will give me the alkyl bromide. You could tell here, even though there's a tertiary carbon next to it, there is no carbocation formation. All of these methods, whether you're using a primary alcohol or a secondary alcohol, all of them are SN2 mechanisms. None of them going to give me a carbocation. And this is important. That's the difference between the method of HX and the method of phosphorus X3. Here's another example. So I have a primary alcohol in presence of phosphorus iodine. What do I get? I get an iodide product. Here's a secondary alcohol in presence of PPR3. What do I get? I get the alkyl bromide. Here's the mechanism. So if I have PX3, regardless what X is, whether it's Cl or Br or I, what usually happens? Alcohol will attack the phosphorus. So oxygen lone pair will be the starting point of the arrow pushing. So it's going to attack the phosphorus, and that's going to right away kick off one of the Br attached to that phosphorus. What do you end up making? You're going to make this complex. It's an activated alcohol. Again, we're making the OH a better leaving group. In the case of HX, we made H2O plus. In the case of phosphorus, we're making the oxygen phosphorus bond. So that's going to put a plus charge on the oxygen and make it a better leaving group, plus Br minus. Okay, I just mentioned it's an SN2 pathway. So there will be no formation of carbocation. So what's going to happen? Br minus will attack R. That R should be a primary or secondary, and that will give me the alkyl bromide, plus this side product, which is the inorganic product where we have the oxygen being cleaved out of the alcohol structure. Thionyl chloride, SOCl2. Of course, that's when I'm interested to make an alkyl chloride. So primary or secondary alcohol, in presence of thionyl chloride and heat, what's going to end up happening? You're going to end up making the OH substituted with Cl. The good thing about this reaction that you're making actually gaseous products. Those gaseous products are SO2 and HCl. So for organic chemists, reactions that give the product without need of purification, usually it's a good method, actually. And this is one of them. Here's the mechanism of the thionyl chloride. So the alcohol, oxygen will attack the sulfur. Eventually, what's going to happen? It's going to kick off one of the Cl. So that's going to go through the following. Oxygen attacking sulfur, breaking the pi bond between S and O, and then restoring the carbonyl, the double bond. That's going to end up kicking off one of the Cl. So you end up making this activated alcohol once again. And Cl minus is going to grab the hydrogen and it's going to give you this chlorosulfide ester. What's going to happen next? Well, what's going to happen next, that it's going to be a quick, actually, step where most of the time the carbocation is not formed, actually. It will be actually attacked right away with the Cl minus to end up giving you the alkyl halide. What I mean by that, that this could actually end up giving you the final product right away. So the Cl minus attacking R to give you the final product. But sometime, if I have a secondary alcohol and if I have a crowded carbon that's preventing the Cl minus from attacking it, it may go through the carbocation formation first and then wait for the Cl minus to attack the R to give you the alkyl chloride. But most cases, it's an SN2 pathway, whether I use X3 or thionyl chloride. So very important to remember every single time I have a primary alcohol or a secondary alcohol, think of the PX3 method. PCl3, if I want to make an alkyl chloride, thionyl chloride, that's also acceptable as SOCl2. PPR3, if I'm interested in the alkyl bromide, and phosphorus and iodine, if I'm interested to make the alkyl iodide. All of them are SN2 reactions. What if I'm interested to make an alkyl halide from a tertiary alcohol? Don't think of the PX3 alternative. You will need to think of the HX. HCl, if I want to make the tertiary alkyl chloride, HBr, if I want to make the alkyl bromide, and HI, if I want to make the tertiary alkyl iodide. No need to use zinc chloride, because zinc there was the tertiary alcohol. It's a quick substrate to give a carbocation. So what's the need of the zinc chloride? H plus will be enough to kick off that OH once it gets protonated. Next reaction, dehydration reaction. We've seen this in one of the methods how to make an alkene. So the requirement here is temperature and an H plus. So when you have an alcohol in presence of H plus, that will be an acid catalyzed dehydration to give you an alkene. What we learned previously, that when the alcohol is tertiary, it's going to be faster than a secondary, faster than a primary to give the corresponding alkene. Why? Because it's an E1 mechanism. And it's very important that we remember that the OH is a bad leaving group. So it's going to need to be activated, kicked off to give me a carbocation, which opens up the possibility for having 1,2 hydride shift or 1,2 methanide shift to end up basically eliminated next to give me the alkene. Bimolecular dehydration, what that means is that if I have the OH being protonated, temperature control may have the secondary, the other alcohol to attack that carbon to end up giving you the ether product. So that's a method we're going to learn actually in the following chapter, how we make ethers. So we could look at the mechanism then. But for now, keep in mind, acid catalyzed elimination of an alcohol usually goes through a carbocation formation. It's an E1 mechanism. And here's the full mechanism. So you could see the alcohol being protonated to give you the oxonium. This will basically wait for the H2O to be kicked off to give you the carbocation. This carbocation is already the most stable form of this structure. So there will be no 1,2 hydride shift or 1,2 methanide shift. Heat, what's going to push this carbocation to give me the alkene. So you could see here that if I don't have heat, water will probably just attack the carbocation and give you an alcohol at the end. So you're going to need heat to push the water to abstract a hydrogen from the adjacent carbon to give you eventually the alkene structure. And let me remind you, tertiary alcohol will be faster than a secondary, faster than a primary to give me the corresponding alkene. You can see here the E1 mechanism. So we could see that the alcohol will be protonated to give you a protonated alcohol, and that will give me a carbocation, and eventually will be waiting for the water to abstract the hydrogen from the adjacent carbon to give you the alkene. It's an equilibrium reaction, will be pushed using heat. That's how we push. And of course, excess of the acid will actually push the reaction to go forward. You could see here clearly the energy diagram, that alcohol to give me the protonated structure will be very similar in terms of energy level. So that's a fast step actually. What the rate determining step will be the generation of the carbocation. And the carbocation, the reason why it does have another transition state, that's if there is a 1,2 hydride shift or 1,2 methanide shift, because the formation of a more stable carbocation will be always at a lower rate, at a lower energy. That's why it will be favored to form it. And once it's happening, it will go through the elimination at the end to give you the alkene faster than the prior rearranged structure. Predict the product of sulfuric acid catalyzed dehydration of 1-methyl cyclohexanol. So this will be going through protonation, give you a carbocation. Once you kick off H2O, and you end up basically having the possibility of eliminating the hydrogen from the secondary carbon, and that will be the major product, because every single time you generate an alkene from an alcohol, you're always going to generate the Zaitsev product. That's important, the more substituted alkene. The other possibility, of course, the minor one, picking a hydrogen from the primary carbon to end up making the terminal alkene, the methylene structure. So this will be the minor product. And this is the bimolecular condensation that I was referring to, that you could make alcohol in presence of an acid, giving you an ether somehow. Well, of course, the temperature control will be the one that's going to push this to be formed. And usually, primary alcohol are the ones that we may expect actually an ether formation to come from. Why? because alcohol, once it gets protonated, the primary carbon allows for a nucleophilic attack. So another molecule of the same oxygen will attack that carbon, kick off H2O, and that will give you the protonated ether, which will wait for the medium to pick up that acidic hydrogen to give you the neutral ether. So it's an SN2. It's called bimolecular condensation to form ethers, and you can see here it's an industrial pathway. If I'm interested to make an ether, I wouldn't go grab an alcohol and throw in H plus and heat. Why? Because I can't control the reaction to go toward ether versus toward alkene, because you've seen that 180 degree versus 140 degree. Well, sometimes the nature of the alcohol, it may actually give you an ether above 180, or I may get an alkene below 140. So that's not a reaction that I would do in a lab setting. Rather, I will do it industrial application. We will learn actually how we make ethers in a much better route than the bimolecular condensation. So once again, if I have an alcohol, H plus and heat, secondary alcohol and tertiary alcohol will give me right away an alkene structure, E1 mechanism. Primary alcohol may give me an alkene as a major, and may give me also an ether as a minor product. And the minor, and it's important that we keep in mind E1 mechanism for the alkene formation and SN2 mechanism when I have an ether coming from alcohol, primary alcohol. Next reaction has to do with diols. We have learned methods how to make diols from alkenes. We've seen the method of osmium tetroxide and hydrogen peroxide. And we're also seeing the dilute KMnO4 method also that can give me a syn diol. Now, vicinal diols can undergo one of those two reactions. Can undergo pinacol rearrangement or periodic acid cleavage, so HiO4. Pinacol rearrangement to give me pinacolone, it's actually an interesting reaction. Only happens, of course, those two reactions only happen when you have vicinal diol, not geminal diol. Vicinal diol, that means I have two OHs on two adjacent carbons. So what's going to happen? In presence of sulfuric acid and heat, I'm going to see a diol giving me a ketone structure. So what you end up doing, actually kicking off one of the OH, not only that, CH3 will be rearranged to the other carbon. So how is that going to happen? Well, keep in mind that the motive here is to form the ketone structure. So as it is going to be a more stable structure than the diol. So how is that going to happen? You will protonate one of the OHs. So it's a strong acid being used to protonate one of them. And once you do that, you're going to end up making the protonated OH, giving you a carbocation. Once you form the carbocation, the CH3 that's on the carbon that has the OH will rearrange. And the reason why it rearranges because of the next step. And we'll see what that next step is. That CH3 will rearrange or migrate to the carbocation. So it's going to give you basically the terbial moiety attached to a carbocation that will be stabilized by the oxygen lone pair. Here, the carbocation stabilization is because of the sp3-CH bonds. But here, what the stabilization is happening by the lone pair that's sitting on the oxygen. So that's what actually pushes this step to happen, the migration step. And you could see here the two resonance forms because of that stabilization effect. Once you have that, you can end up making basically the pinacolone by having the medium abstracting that hydrogen from the protonated ketone. And the pinacolone is the outcome of the pinacol rearrangement. And again, this is usually a reaction that we notice not only for pinacol, for anything that does have a vicinal diol moiety, that you end up making a rearranged after you generate the carbocation, and then you form the ketone structure. The other reaction that's also important when we have diols is the periodic acid cleavage of vicinal diol. And we could see here clearly that the C single bond C is going to be cleaved, forming two carbonyl structures. And this will be similar to an ozonolysis outcome. So there you break a C double bond C to form two carbonyl. The side that has a hydrogen, you will end up making an aldehyde. The side that doesn't have a hydrogen, you may end up making a ketone. So just keep that outcome of ozonolysis of ketone, of alkenes, when you think of the periodic acid cleavage. So this reaction will go through. We already know that diols can be made from alkenes, and preferably to be a cis, of course, diol. So the two methods that we have learned, the KMnO4 dilute and the osmium tetroxide hydrogen peroxide. Once you react that with HiO4, what's going to happen? You're going to form a periodic intermediate. So you can see here that the two oxygens are still there. You didn't cleave the C single bond C yet. So when you end up making this intermediate, and once you form that intermediate, you end up making a double bond on the right-hand side of the CO. That will make, because of the fact that it doesn't have a hydrogen, you end up making a ketone moiety. And the left-hand side, because there's a hydrogen, you end up making an aldehyde. So it's an oxidative cleavage of vicinal diol that will end up giving me two carbonyl structures, or two carbonyls moiety. The side of that vicinal diol that does have a hydrogen will end up be the aldehyde. The side that doesn't have a hydrogen, the substituted one, is going to end up making the ketone part. Another reaction of alcohols is esterification. And the only mechanism that you are required to know is the very first one, which is the Fischer esterification. So we can make esters, we could make tosylate esters, we could make sulfate esters, we could make nitrate esters, and we could make phosphate esters. What is this reaction about? This reaction, which is esterification, usually reacts a carboxylic acid with an alcohol. You end up grabbing the hydrogen from the alcohol and the OH from the acid to form H2O, and then link the two together. So the acid carbonyl will end up basically attached to the oxygen of the alcohol. And that's what you see here, the ester structure. Catalyst is important, H+, and we will see the full mechanism, which is required actually. And this reaction actually requires heat most of the time. So it's an equilibrium reaction that you're going to need to push it, not just using catalyst, but sometimes using excess alcohol and heat. So we learned from the Gen Chem Le Chatelier's principle that when you have an equilibrium, you always want to push it to the right using excess reactants or abstracting one of the products to prevent it from going backward. So that's what's happening here. We use excess alcohol. We heat the reaction to basically overcome the equilibrium point to get to the product side. Otherwise, if I run it at room temp, if I don't use excess alcohol, I will end up making 50% or maybe less reactants, and 50% product will be useless to do that. Here is the some examples. So we could see that acetic acid plus ethanol in presence of H2SO4, that will give me, I mean, it's favored to go to the right. So 3, or actually to the left as well. So we could see here that you form basically an ethyl acetate. So it's an ester product. What if I have a diacid? Excess alcohol and H+ will push it to the polyester or diester in this case. The full mechanism is going to go through the following steps. The very first step, remember, you have alcohol, you have a carboxylic acid, you have an H+ catalyst, usually sulfuric acid, and you have the ester and water as products. Carboxylic acid will be protonated. Carbonyl oxygen will be more basic than the oxygen of the OH. So that's why the oxygen of the carbonyl will be the one, because it's more polarized. Electron density is more towards that oxygen. So that's why that oxygen will be the one that's going to grab the hydrogen. So you're going to end up making the protonated carboxylic acid. Much more reactive. What is that acid going to react with now? It's going to react with the alcohol. So the O of the alcohol is going to attack the carbonyl, and that's going to give you the tetrahedral structure that you see here. And this structure, what you end up forming next, I mean, keep in mind that one of those two OHs, one of them is going to end up leaving as water. So this hydrogen that you have on the oxygen coming from the alcohol is going to end up being transferred to one of those OHs. So that's the goal. So how's that going to happen? Well, the medium alcohol will grab the hydrogen from the protonated oxygen of the alcohol side, and then it's going to give you this hydrate, and this hydrate will go through protonation to protonating one of the OHs to give you basically the protonated OH, and next delocalization of the OH to give you the carbonyl, and that will be the protonated ester. So remember, you have a protonated carboxylic acid, alcohol attack, H of the alcohol that came in will be transferred to one of the OHs. So that's what's happening here. And eventually the carbonyl of the ester will need to be made. So that will be coming from one of the oxygen, which obviously is the O of the OH. And once you form that carbonyl, that hydrogen will be abstracted by the medium, which is also alcohol, and that will give you finally the neutral ester plus H plus. That will be the catalyst. We have to recover it back as it's a catalyst. It's not a reactant to give you a different product. So that's basically the mechanism of the Fischer esterification. Protonation, the carboxylic acid, attacked by the alcohol, proton transfer, eventually kicking off water to give you at the end the ester structure. Another way of making ester is instead of using carboxylic acid, we would use the acid chloride. This is a much faster reaction than the Fischer esterification, and there are reasons for that. Because one, carboxylic acid has an OH that's a worse leaving group compared to the Cl. So the acid chloride is much more reactive than carboxylic acid. So we will notice here actually, there is no use of H+, and there is no heat required to push this reaction forward. So that's why the alcohol plus acid chloride, all what you need is a pyridine. What's the pyridine for? Pyridine is to neutralize the resulting HCl, because if you have it around, you may end up pushing the reaction backward. So because of the Cl minus being actually a good nucleophile. So that's, or a moderate nucleophile. So that's why you want to prevent that from happening. How do you prevent it? Use a base that will neutralize the HCl. So alcohol plus acid chloride, you end up making oxygen bonded to the carbonyl, generating HCl, which will be neutralized by the pyridine. So the ester will be the product of this reaction. Here's some other moieties that you could make esters out of. So if I take, for example, this glycerol reacting with nitric acid, all of these reactions of esterification, we always going to generate water. H from the alcohol and OH from the acid. If it's a carboxylic acid or a nitric acid or sulfuric acid or phosphoric acid, as we're going to see next. So nitric acid, OH, will be eliminated with H of the alcohol, and that will end up making basically water. So what you're going to end up making on every single OHN, well, the oxygen will become bonded to a nitro. That's from the nitric acid, and the same applies to other OHs. So that's just important to keep in mind how nitrate esters are made. Phosphate esters, same route. So if I take the phosphoric acid, how many OHs do I have? I have 3. That means I can react phosphoric acid with 3 different alcohols. The first one is going to basically generate water from OH and H from the alcohol, and that will basically insert the first RO, so OCH3 in this case. Take that monomethyl phosphate, do it again. So that's going to give me the dimethyl phosphate. Do it 3rd time because I still have an OH. That OH will leave with H of the alcohol to give you the 3rd methoxy. So that's going to end up making the trimethyl phosphate. So that's important to keep in mind how we make phosphate esters. So esterification, as I mentioned, the most important mechanism that is required is the Fischer esterification. The last reaction is the Williamson ether synthesis. We're going to see this reaction in the following chapter, how to make ethers. So it's an important, actually, that it appeared here so that we remind ourselves later with this reaction. We've seen that alcohol is a bad electrophile, and it's a weak nucleophile. That's what we already learned previously. Alcohol can be activated and made a good nucleophile by deprotonating the OH using sodium, using lithium, using potassium, using sodium hydride. Once we make the alkoxide, this alkoxide becomes a strong nucleophile. If I react alkoxide with a primary halide or tosylate, that's the best method to make an ether structure. So we go from an O- attacking the carbon X, and that will end up go through an SN2 pathway. And of course, if there is a stereo definition, it will actually be the inversion of configuration because it's an SN2 pathway. What if I have a secondary halide or tosylate? What if I have a tertiary halide or tosylate? Less likely it will give me the ether. It will actually give me the alkene. So those alkoxides will behave as bases rather than nucleophiles in the case of secondary or tertiary halides or tosylates. So that's important to keep in mind. Only primary halide to be used if my goal is to make an ether out of the alkoxide. And this is the story of chapter 11.